Okay, welcome. Sorry for the delay there. I actually made a mistake and started the wrong meeting. And fortunately, you all were here ahead of me. All right. It is time to get going. And today we are going to be looking at section 1.5. Someone mentioned to me just before class that I had not posted the 1.5 notes yet. So, oops, sorry, they will be up tonight. They're written. As a matter of fact, I'm going to be pointing to them here. It is just possible I might be able to post them soon enough to be of use if you have access to Blackboards. Let me just take a quick look. If I can pop them up there in a hurry, I will. Probably a bit late to print them out, but if you wanted to look at them on screen, this would help. Yes, those are the ones. You can't see this. I'm getting the little, I'm working on it circle. Okay, finally. Everything takes longer when you're in a hurry, right? Okay. Almost there. Oh, that's the recording, right? Okay. So let's see here. You need this. And I think it's probably there. Woohoo, it is. All right. If it's helpful to you to pull that up on screen while we're working, that would be fine. This is not supposed to be showing. And I think we're ready to start. Let me mention one thing before I start with the lecture. And I need to switch my camera here. Okay. So the thing I just uploaded online was this document right here. And I should probably mention this right at the beginning of the course, where I'm doing things like teaching you how to solve systems of linear equations. I know a lot of people don't really need much help with that, and so they might not pay a lot of attention to the handouts. But as we get further and further in this, there are things in the text here that I don't have time to say in class. So I do recommend that you read them. Okay. Now, if you read them online or you print them out, whether you bring them to class, whether you use them to take notes, that's totally up to you. But it's like a textbook. Generally, there's expectation that you would familiarize yourself with content in the textbook. One other thing I want to say is I have, or I will, I have written the, I've written up the second hand-in assignment. It's not yet posted. It takes, there's a lag between when I can write and when I can post, but that'll be posted later tonight. Also, all the homeworks that came in the usual way have been graded. If yours hasn't come back to you by email yet, it will tonight. So I'm gonna finish scanning and emailing those, so we're pretty well done with that. And the last thing I want to mention is that this time on the hand-in assignment sheet, I actually start listing some requirements, some standards for how you should write. And I'm always a little bit hesitant when I do that, because it can come across as kind of heavy-handed, and I don't mean it that way at all. I'm trying to just teach you what the common standards are for writing mathematics. And when you read through it, you'll see what I've said, and most stuff, is kind of common sense. Put your problems in order, and write on white paper, and just stuff like that. There is, though, some people have trouble with this. Most people don't. They catch on with just a little bit of coaching, and that's really all I'm trying to do, is to coach you along in good writing habits. But what happens if someone doesn't come along with some coaching? Well, the first time, if somebody just makes a small error, I mean, we all do that, right? So I don't jump on it. If I see it, I'll probably mark it, but that's it. I just mark it, and hopefully you notice and become sensitized to that and avoid that problem in the future. Sometimes, though, people are actually making systematic errors, and it's usually not because they're trying to make a mess of their paper. They think this way of doing it is okay, but most of the world would not agree. So, at that point, I write a note, and the first time something like that happens, there isn't any penalty. I'm just trying to coach you. Don't. This is not a good way to write. How about something like this? So that's it. If you get the note, unless there's some further note that says I took off 2 points or some such thing, then there's no penalty. I won't even remember, probably. Um, if someone isn't responding to coaching, it's at that point that I might take a point or two off, just to kind of reinforce the idea that it really is important how we write. And the highest level of correction would be this. If I consistently get papers from someone that I just, it's just laborious for me to figure out what they meant, then I would say, I'm sorry, but from now on, you're going to have to type up your assignments. I know. I see the raised eyebrows. Well, I have some good news for you. I've been teaching on the order of 40 years. And I know you look at me and you say, gosh, he only looks 35. How could that be true? Well, okay, 65. I actually started teaching before I graduated from high school. So I really did. The high school said, gosh, we got these people who really need help and we don't have time to help them. How about you? Would you help? So I said, sure. So in around 40 or more years of teaching, so far, I have never had to require anyone to type their assignments, okay? And the reason is most people want to do well and they're, with a little bit of coaching, they do great. And once in a while, someone loses a few points, but it's just never gone beyond that. However, if you really can't write, then I'll ask you to type, all right? But don't worry that that's going to happen. I really don't think it will, but it could. So anyhow. All right, that's probably all I need to say by way of introduction. And I'm ready to start 1.5. This is a little bit shorter section, but it is not light. This is starting to get a little bit deeper into the critical ideas in linear algebra. And the good news is after this one, I think there's just one more. And then that's it. We're done with our survey of linear algebra because we are not trying to deliver a whole course here in linear algebra, trying to give you just enough so that you can make use of it in solving differential equations. So we've come really a long way so far, and that's great. However, I am not insensitive to the fact that this moves very rapidly. So if you need help, or even in a lecture, if I'm doing something and, you're feeling just overwhelmed, like, oh my gosh, what is this guy talking about? It would be a good idea if well, because of the way we have to deliver this, unfortunately, my attention is kind of right here on the paper. So whether you're joining us online or you're joining us in the physical room, honestly, I might not mention, I might not notice if you're waving your hand trying to get a hold of me. So just say something. I, I, I don't take that as being impolite. If you say, oh, I'm not with you there. And then I'll stop and say something like, oh, where did you lose me, or something like that. And I really will try to help. If I can't help in a reasonable amount of time during lecture, I really am happy to stay after class, whether you're online or whether you're here in the physical room, it doesn't matter. I really want to help you. I want you to learn. And for this to be as good of an experience as it can. On the other hand, when you get two courses crammed into one, it's going to be sort of like, what do they say? Getting a drink out of a fire hydrant. It's it's just a whole lot all at once, right? And I understand. I have often wondered myself, how well would I have done as an undergraduate if I had been given it this way? Because I wasn't. I got a course in linear algebra and I got a course in differential equations, and so I did not have to deal with it this way. Okay, today we're going to be talking about linear transformations. And linear transformations are a certain kind of vector function. So what we're thinking of is this: you're given a vector in some vector space, and then this function does something to it and it produces a new vector. Now that new vector might be in the original space you started with, or it might be in a different one. So for instance, you could have an input that's a 3-dimensional vector and the output could be a 2. And as a matter of fact, we do that all the time. I might almost be able to picture it here reasonably well. So if you sort of think of my pen as a vector, uh, and it's probably harder to see online, and maybe from the back of the room, not just hard, but impossible to see. What I'm doing is I'm kind of sticking the vector up at an angle on my paper, and there's a shadow down here. Well, this is what's called, officially, it's called a projection of this vector from 3 space down to 2 space. And it's essentially what casting a shadow does. So the function in that case is, in fact, one of these examples of a linear transformation. And it takes a vector, any vector from 3 space, and turns it into a vector in 2 space. So that would be an example of the sort of thing that we're thinking about. There is some notation, and I hope it looks okay on the screen here. I hope for people joining us online, you can see I've highlighted some things here. But keep in mind, I will scan this document and post it. So if online you can't see the color, you will be able to see it in the scan that I post later tonight. T is a linear transformation. V is the input vector. And it turns out that for what we're going to define as a linear transformation, every single time without exception, you can construct that function by left multiplication by an appropriate matrix. So any linear transformation can be written as a matrix multiplication, and every matrix multiplication, left multiplication by a vector on a vector, is also an example of a linear transformation. So they're in one-to-one correspondence. Linear transformations are matrix multiplications, and matrix multiplications on a vector are linear transformations. So sometimes you'll see it written that way. Now, in that spirit, you'll also sometimes see T of V. Instead of writing it that way, people will write T times V, sort of like T were a matrix, so that it looks like matrix multiplication. Well, there's a good reason for that, and that is that you can write it as a matrix multiplication. So it's sort of like when we're thinking about vectors, sometimes with vectors, we write them as row vectors, and sometimes we write them as column vectors, and we're just kind of oftentimes a little bit muddy about, which format you're supposed to use. We just sort of go back and forth. And sometimes we look at that and think, oh, those are the coordinates, say in 3 space. And other times we look at it and think, oh, that's the vector. Well, you just kind of figure it out from context. So people do that with linear transformations as well. Now, what is a linear transformation? Well, here's the official definition. A linear transformation is any function t that operates on vectors from one vector space V and produces vectors in another vector space W. Now, V and W may be the same or they may be different. Furthermore, the function t has to obey the following properties in order to be called linear. Given any 2 vectors u and v in the source vector space, that's the domain, and any scalars k, c1, and c2, then these 2 properties have to be met. The transformation of u plus v has to be the same as the transformation of u plus the transformation of v. And if you think of that as a matrix multiplication, it says the distributive law works. Okay, so you would kind of expect, if these things could be represented by matrix multiplication, that would have to be true because we do have a distributive law. Furthermore, the scalar times v If you transform that, you get the same thing as if you just transform V and then multiply by a scalar later. Now, you can write these two requirements with a single requirement that wraps it all up. So this is an alternate version of 1 and 2. Given two scalars, C1 and C2, and two vectors U and V, the transformation of C1U plus C2V is the same as C1 times the transformation of U plus C2 times the transformation of V. But I want to emphasize, we don't, if we're trying to show something's linear transformation, we don't show that 1 is true and then show that 2 is true and then show that 3 is true. No, we would either show that 1 is true and that 2 is true, or we would show that 3 alone is true, because 3 combines the requirements of 1 and 2 together. So it's optional. You could do it the first way, 1 and 2 separately, or the second way, you could do number 3 all by itself. But it would be redundant to do all 3 of them. It's just not necessary. Okay, there is some vocabulary here, and honestly, I'm not big on things like vocabulary quizzes. However, when we're talking about this, we end up using the language. So if nobody ever says what we mean by it, well, that would not be very helpful, right? So if we will write this kind of a symbol right here, T:\V arrow W. That means this. T is a linear transformation that takes a vector in V and produces a vector in W. But that's not what a mathematician would say. He or she would say T maps V into W. We'd also say that if you start with V and apply the transformation T, you end up with W. We say that W is the image of V under T. Why under? I'm not sure, but that's the tradition. So it's the image of V under W. Okay, and it's common, as I mentioned before, to see that written as TV rather than T of V. And the reason is that this transformation, you could come up with a matrix that would do it. And if you called the matrix T, then T times V would indeed be the image of V under transformation T. Okay, so for an example, suppose we want to cook up an example, a linear transformation that takes a vector in R3 into R2. It just occurred to me, oh, we're all set. I couldn't remember if I turned the recording on. And well, we know that there's a one-to-one correspondence between left multiplication by a matrix and linear transformation. So one way of inventing one would be just to come up with a coefficient matrix, right? Now, notice I didn't use a 3x3 here because I wanted my vectors to start in R3 but end up in R2. So this is a perfectly good recipe for a linear transformation that takes a vector in R3 and produces one in R2. Now, just so that this isn't overly abstract, I didn't leave space, but I'll give you an example. What do we have here? 1, 1, 0, minus 1, 2, minus 2. Oh, I don't have a backside of that piece of paper. Working on it. So, for example, T of V is supposed to be left multiplication by the matrix 1, 1, 0, minus 1, 2, minus 2, and then you multiply by anything in R3, and you're going to get something in R2. So let's take an example. How about this? I'm going to take the vector, and just to emphasize that we don't always want to be chained to the vertical format for writing vectors. If I wanted to do this, I would say, well, I need my transformation matrix 1, 1, 0, minus 1, 2, minus 2. I multiply that, and now I do want to write it as column vector, 3, minus 2, 1. And what's going to happen? I'll have 3 minus 2 is 1 plus 0. And here I'll have 3, minus 3, minus 4 is minus 7, minus 2 is minus 9. And if I did the arithmetic correctly, then you could say that this vector 1 minus 9 is the image of 3 minus 2, 1 under the transformation T. Okay, so that's not supposed to be deep, but just to make clear what we're talking about. These are the kinds of functions that we're working on. Now, there is a little bit more notation. Sometimes we really do want to be clear about the distinction between the function, the linear transformation, and its matrix. And if we do that, then I would write something like that. That T is the linear transformation. Which after all is a function. And if I were trying to distinguish between the function and its matrix, then I would probably write this. That's the matrix of the linear transformation. Now, it's not very often that we really want to be that careful. But if I wanted to use notation that really was precise and distinguished between the two, then I would do that. This is the function. This is its matrix representation. In this case, it would be that matrix right there. Yeah, and there's, the difference is a little bit subtle, right? With a function, we're just thinking about, it's a rule that takes a certain vector to another vector. And this means, well, that's the matrix that accomplishes the rule if you multiply it on the left. But usually we don't bother. But we could, if there were ever a reason to really distinguish, then we would do something like that. And this can actually come in handy because if you think about it, well, it's probably not obvious right now, but there's more than any non-trivial vector space has more than one basis. And it turns out that the matrix representation is tied to the basis that you're working with. So if I had two different bases, then I would put like a subscript on there that would say, when you're working in this basis, this is what the matrix looks like. When you're working in another basis, it'd have a different subscript because the matrix would look different, but you don't need to worry about that right now. We'll get there later. Okay, so that's this thing right here. The matrix of the linear transformation can be symbolized with the name of the transformation with square brackets about it. Okay. Now, we can infer from the contents of the matrix of the linear transformation, how it acts on a standard basis. And let's just do that. So this is the very one that we were looking at just on that other piece of paper a moment ago. Suppose we set the input vector to be the first standard basis vector, 1, 0, 0. Well, if I take that product, what's going to happen is this 1 is going to multiply the first column here. 0 is going to multiply the second column. 0 is going to multiply the third column. It's just going to pick off the first column. Likewise, if I multiplied by the second standard basis vector, the one we call E2 usually, it would pick off the middle column here. And if that's not obvious, let me step through just one more. Let's do this multiplication to get that element right there. You get 0 plus 1 plus 0, it'll turn into 1. And here you get 0 plus 2 plus 0, you get the 2 there. So notice it copies that middle column over here. And likewise, T of E3 is going to give you the third column right here. Well, goodness, we just got a recipe. If you know how a linear transformation behaves on a basis of the vector space, then you can immediately write down its matrix representation. So if I know that T maps E1 into 1 minus 1, it maps E2 into 1, 2, and it maps there is an error here. That's supposed to be a 0, and that is supposed to be a 1. And it maps E3 into 0 minus 2. Well, I just stack those images up as columns, and I now have the matrix of the linear transformation. And if you think about it, it's even more powerful than that. What we're saying is, if you know what a transformation does on a basis of a vector space, you can compute what it does on any vector. Why? Because you could use those first 3 bits of information in this case to create the matrix. And now anything else I just do by matrix multiplication. So for instance, T is going to map R2 into R4. So that means it's going to take 2-dimensional vectors as inputs, and it's going to produce 4-dimensional vectors as outputs. So let's use that to compute the matrix, and then I'm going to show you how to compute T of minus 3, 2. Okay, so first of all, I know this, T of 1, 0, E1, and I suppose officially I should use double parentheses here, but that's pretty inconvenient. So, but I do want to write this as a column because that's how I'm going to use it. That image is 1, 1, 0, minus 2. T of E2 is 0, 0, 1, 3. And for R2, that's all there is to a basis. E1 and E2 is it. So the matrix of the linear transformation, now I'm writing it this way only because I'm emphasizing I want to be able to write down the matrix. It's going to be this. It's T of E1 as a column and T of E2 as a column. And now I can answer this question quite easily. What is T of the vector minus 3, 2? Well, my answer to that is, well, I know what it does to the standard basis. That allows me to write the linear transformation as a matrix multiplication, minus 2. And now I just write that input, minus 3, 2, as a column vector. and I do the matrix multiplication, and I'm done. So it's going to be minus 3 plus 0, minus 3 plus 0 again, 0 plus 2, and let's see here, this is 6 plus 6, 12. Okay, so if I know what it does to the basis, standard basis, boom, I write down the matrix of the linear transformation. And now if you want to know what is the image of any other vector in T2, well, I just do a multiplication and I'm done. Okay, any question about that? Now it just strikes me that I could push this just a bit further. By the way, I wouldn't necessarily, if I were writing on the board, I wouldn't bother to put stuff like that in here, but I'm aware of the fact that this gets posted, and like if somebody had to miss class, it would really be kind of nice if they could figure out what the notes meant. Okay, so let's do this another way. There is another way. I have this property of linear transformations in general. Where is it? Right here. T of C1U plus C2V is CT of U plus C2T of V, right? So I'm gonna use that to my advantage here to find another way of computing this transformation right here. So I really don't need that right now. Okay, so I'm gonna look at minus 3, 2, and I'm gonna write that as a linear combination of the standard basis vectors, not plus equals. Well, once you realize what thing I have in mind, you realize, oh, that's like instant. You don't have to do any calculation at all. If I take minus 3 times E1 plus 2 times E2, I do get that, right? So I should be able to do this without matrix multiplication as well. What is T of minus 3, 2? Well, one way is to do it by matrix multiplication, and there's nothing wrong with that. As a matter of fact, it's pretty efficient for calculation. Probably that's what I would do if nobody told me to do otherwise. But here is another way that would work. The rule says that's supposed to be the same as this. Just write this input now as a linear combination of the basis vectors. Minus 3, 1, 0, plus 2, 0, 1. So far, I've really done nothing that's used the theory of linear transformations, but now I'm about to, because the rule says this. One way of reading this is this: the transformation of a linear combination is the linear combination of the transform vectors. So I can apply T first, and I'm leaving a little space here. Apply T first to 1, 0, and then multiply it by minus 3. And then likewise apply T first to 0, 1, and multiply it by 2. That's what it means to be linear. Okay, now let's go back to our description. The description tells me that T of the first standard basis vector, T of E1 is 1, 1, 0, minus 2. plus 2 times, and since it's linear, I can just process E2 on its own. And the instructions were, this is supposed to be an E here. T of E2 is 0013. And now I can multiply these out. Okay, -3, -3, 06. And multiplying by 2, I get 0026. And when I put them together, I get, let's see, -3, -3, 2, 12. And what did we get the other way? Right here. -3, -3, 2, 12. That's what we did. That's what we got when we did matrix multiplication. And this is what we got when we used the definition of linear transformation. So it worked. Okay. So why would anybody ever care that their transformation is linear? Well, one answer is, well, so you could do this sort of thing. All right, so there is an introduction to what we mean by linear transformations and a little bit about how you could do calculations involving them. Okay, page 3. And now we start heading towards the drop off. If you grew up in Michigan, you probably know about that. There's certain places where you can go swimming and, you know, it's nice and level and just slowly, gently getting deeper. And then you take one more step and you're underwater, right? And hopefully you can swim, or at least are nearby somebody who is really good at swimming. So we're getting close to the drop off here. All right. Changes of basis from, now this means these are names of bases. So suppose S is the standard basis. That's what I have in mind when I wrote S. And B is just some other basis. Okay, we noted earlier that every vector space with a dimension of at least 1 has to have more than one basis. A basis is a linearly independent and spanning set of the vectors in the space. So for instance, both of the following are bases of R2. This one, and you know, sometimes, a lot of times we call that E1 and E2. That looks like 0 sub 1. It's E1. And that's E2. That's the standard basis. But here's an alternate one. This is a perfectly good basis. The span of this set is all of R2, and they are linearly independent. You cannot take a linear combination of 1, 1 and produce -1, 1. Though those two are not dependent on each other. It's pretty easy to check that these are both bases. Why? Well, you could write, say, this one, these vectors you could enter as, well, you could think of them as columns or rows. You'd get the same thing. Row reduce it and you just get the identity. As a matter of fact, you started with the identity. So row reducing doesn't do anything there. But in this case, you could take 1, 1, enter it into the matrix, -1, 1. And if you row reduce that, you'd find out that you get to the identity, which tells us that those two vectors in two space are linearly independent. And there's a theorem that says if you have n vectors in an n-dimensional space, that are linearly independent, they must also span the space. So that means it's a linearly independent spanning set, it's a basis, okay? So this is a basis of R2, and this is a basis of R2. Now, that means that any vector in R2 can be written in one and only one way as a linear combination of vectors in S. But the same is also true of the vectors in B. So for instance, let's take this vector right here, -1, 5. If you took 2 times 1, 1 plus 3 times -1, 1, well, let's just check it out. You'd have 2 minus 3 is -1. 2 plus 3 is 5. Sure enough, -1, 5 is a linear combination of these two vectors here. And since I would like not to have to say their contents all the time, I'll call them B1 and B2. So -1, 5 is a linear combination of B1 and B2. Why? Well, B is a basis of R2. So that should be the case. Of course, you can also write it as a linear combination of E1 and E2. Why? Because E1 and E2 form a basis for R2. Now, that means, well, one way of interpreting that is this. -1, 5 has coordinates -1 and 5 relative to the standard basis. It has coordinates 2, 3 relative to basis B. And at this point, most people start getting uncomfortable. Wait, I thought the coordinates of a point was just a fixed thing, right? So if I go out 3 units on X and 2 units on Y, what I say, 3, 2, and down 1 unit in the Z direction, the coordinates of that point are 3, 2, -1. Yes, that's correct, relative to the standard basis. But it's also true you could do otherwise for a non-standard basis. And for people who are watching online, I'm actually, I need to pre-apologize. I don't know if you're going to be able to see this, but what I want to suggest is this. And if I were coordinated normally, it would be even better. But, you know, I'm not. This is why I became a mathematician, because there were just not that many things I could do. And anything requiring a really great coordination was off the list. All right, so this is supposed to be a picture of like XYZ coordinate axis, right? So X, Y, and up here, Z. Now, if you think about it, that makes, if I line it up sort of in the standard way with the paper, this makes a perfectly good set of coordinates. But what if I sort of twisted it around in space? I could still use these things to identify vectors in space, right? If I have a point over here, well, you're going to have to go out a certain distance along the purple pen, along the purple pen, a certain distance along the red pen, and a certain distance along the blue pen in order to get to this. Where'd my finger go? There it is. In order to get to the point in that space. So the idea is a point can indeed have multiple coordinates. As a matter of fact, for every single basis you specify, you get coordinates. The coordinates are nothing other than these multipliers on the basis vectors so that you get a linear combination that adds up to what you want. Okay, so okay, so you can have, you can describe a point in more than one way using coordinates, and you can do it by switching bases. And that is what this part of the lesson is about, a change of basis. All right, now we know that relative to these two bases here, the standard basis and this vector, this basis B that has 1, 1 and then -1, 1 as its basis vectors, we know that a certain vector, which we're calling V, could be described as -1, 5 relative to the standard basis and 2, 3 relative to this alternate basis B. And you can also look at this as matrix multiplication. In other words, as a linear transformation. So if I take -1,5 and I multiply it by the identity, which is, by the way, the matrix corresponding to the standard basis, I get -1,5. But if I take 2, 3 and multiply it on the left by this guy, which is just using these basis vectors as the columns of a matrix, then I also end up at -1,5. Okay? So 2 sets of coordinates, -1,5 and 2, 3, describe the very self-same vector v, and the vector v is the vector that has coordinates -1,5 in the standard basis. That's the one I have in mind. Okay. So what does equation 1 tell us? Well, it tells me this. If I take, okay, now I've got a new notation here, which I guess I didn't explain. V is the vector, square brackets V with a subscript S means it's the matrix, the column matrix representing V in the standard basis. And really, I should maybe be a little more clear. It's the column matrix for V standard basis. But likewise, I could write V with its coordinates relative to basis B, and that's how that would be this: V square bracket subscript B. So that is the, I won't say column because I don't have room. It's the matrix of V relative to basis B. Now, here's the equation. This thing right up here. It says that V is equal to the standard basis matrix, that's just I times the coordinates of V relative to standard basis is equal to the matrix corresponding to basis B times the coordinate vector relative to B. Now, this is really useful. It doesn't look like it right away, but because these things are bases, they're linearly independent, so that they're giving you matrices that have inverses. So if I were to multiply this equation on the left by B inverse and simplify, I would get this: B inverse times the coordinate vector for V in the standard basis is the coordinate vector for B in the alternate basis B. Okay, and there's a lot of words there, but do I need to, I think it's a good time for an example is what I think. So, yeah. The way we describe it is changing. Yeah, let me see if I can think of a practical example. Suppose that you're a fighter jet pilot in peacetime. We don't want you to get smushed. And you are flying some straight trajectory. So you're flying along a certain vector, okay? Now, as you're flying, and for the benefit of the people who are watching from online, I am going to say, you know, that's kind of big, isn't it? Here we go. Here is what my jet looks like. So I'm flying along here. Now, it's a training exercise. So the commander says to me, okay, Sprague, do a roll. So now I roll my jet along here while I'm traveling along. Now, relative to this coordinate system that I'm thinking of, while I'm shooting up here, I'm thinking straight ahead, that's like my X. I could turn left or right, that's my Y, or I could, you know, go at a right angle to this trajectory that would, if you do it in the right way, give you your Z. And so from my experience in the aircraft, I'm just rotating along this x-axis, the one that is parallel to the direction of flight. But from somebody observing from the ground, it don't look that way, right? Hey, this guy is, you know, you sort of think of it in two dimensions. As suppose the ground level is along here, as he is climbing, he is also doing a roll. So that would be an example where you really, the two different coordinate systems would actually mean something physically. Okay. Yes. Well, each one of those systems of measuring where you're at and which way you're going will generate its own coordinate system. But it's all one path of flight. Exactly. And as a matter of fact, there's a 1-1 correspondence between that. This basis will have its coordinate system, another basis will have its coordinate system. And for any interesting vector space, like 3 space that we live in, there's infinitely many choices for a basis. Now, they're not all useful, but you could do it. Yes. Yeah, that's I can't think of your first name. Yeah, Dustin, let me repeat for people who couldn't hear. He says, well, likewise, you could change to say polar coordinates. And you're exactly correct. Exactly. It's just a different way of measuring where points in space are. And therefore you get different kinds of equations that give you velocity and acceleration and everything that we care about in physics. Okay. So that's what that's what's going on here. Okay, so I was started on something and I have totally forgotten what it was. Oh, okay. So let me give you an example, because you know when I was writing this is the big problem with writing stuff after you've been doing it for 30 years. It's so obvious. Why doesn't everybody get this? Well, you know, I forget. It wasn't obvious to me the first time I heard it either. So, so let's take. Actually, let me take a 3-space example so we can see a little bit better. So there's always a standard basis, and those are just the basis vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. Also, not so much in math, but certainly in elementary physics, very often people represent those as I, J, and K, right? At least they used to. Okay, so that's one basis. I want to write another basis, which I'm going to call B. And let's say that that is the basis that has these vectors. Oh, how about if I just take sort of the complements between 0 and 1? This one is 1, 0, 0. So I'm going to replace the ones by zeros and the zeros by ones. That produces another, it does in fact produce another basis. And I'm doing it this way because I don't want to do something so complicated that I got a quick check. Is that really linearly independent? I want it to be obvious, to me at least. So this is this is a legitimate basis for R3. All right. And in case I need names for, I don't know if I will, I'm going to call this one basis vector 1, the next one basis vector 2, that's this guy, and the next one I'll call basis vector 3. Okay, so now let's pick a point in space. And likewise, pick the position vector that points to that point in space. And frankly, where am I getting this from? Number one, I'm making it up sort of randomly, but I don't want it to be so messy that it's hard to work with. So I'll just say 3 minus 4, 6. That's the point I have in mind. And you could also say this, the vector in the standard basis, the vector that points from the origin to that point in space is 3 minus 4, 6. Okay, so that's what I'm going to call V, but maybe to be really clear now, the matrix, the coordinate matrix, what, not B, S, is this column matrix 3 minus 4, 6. And it means what this always meant to you, even in high school. Go 3 units along the x-axis, go 4 units opposite the direction of the y-axis, and then 6 units in the z-axis. What did I do here? Ah, yes. Thank you. And I have absolutely no good way of fixing that. Unless since I make mistakes so rarely, I have owned this bottle of whiteout for, what is it that I want? I want 110. Actually, last semester. Okay, normally I would have a 1 here, so there I want a 0. As they say in fencing, touche. You scored a point. All right. So there's my B3. And now what I would like to ask is this question. What are the coordinates of V relative to basis cap B? And I guess that's a question mark. Okay, so I know what the coordinates of this point is relative to the standard basis. If I wanted to emphasize that, I could put a subscript S there. 3 minus 4, 6. But what are its coordinates relative to this new basis? Well, the answer comes from, there's actually more than one way to do it, but let me show you this one. Where did my equation go? Right here. The identity times the coordinates relative to standard basis is B times the coordinates relative to the new basis. So I3 in this case times that one. That's the coordinates relative to standard basis. 3 minus 4, 6 is equal to, now I could, likewise, I could say, well, if I took the B matrix, and what's the B matrix? Well, it's the one I get by stacking up these vectors as columns. So 0, 1, 1, 1, 0, 1, 1, 1, 0. And then what are these coordinates? Well, the answer is right now, I don't know. And this is terrible notation. It's technically okay, but it's potentially confusing. Notice these B's do not have vector bars on them. These are the vectors, B1, B2, B3. These are my coordinates, B1, B2, B3. Okay, well, multiplying by the identity does a total of nothing, right? So you just kind of ignore this. It isn't doing anything. If, however, I could invert that matrix, and I can, you can always invert a matrix whose columns or rows come from a basis. They're automatically linearly independent. So I know that if I took the inverse of this basis matrix, multiplied it by 3 minus 4, 6, then I should come up with the coordinates in the new coordinate system. Now, you will all find this very easy to believe. Because I'm such a profound genius, I can look at any matrix up to about a 7 by 7 and immediately announce the inverse. But since you can't, I will put this on my calculator. A couple of people are getting the joke. Probably everyone was. It may be, though, that not everyone thinks it's so funny as I do. By the way, I used to tell jokes constantly in lecture. As a matter of fact, one semester, decades ago, back when it was safe to tell jokes, at the end of the semester, one of my students came up to me and he said, "Dr. Sprague, I just wanted to thank you." And I was expecting him to say, "For such a good course in statistics." That's not what he said. He said, "I just want to thank you for the stand-up comedy." This was the funniest class I've ever taken in my life. So thanks. But have you noticed the way the political climate is now? Almost anything could offend almost anybody. You just don't know. And if I say something now, and of course you all probably would not be offended, you're all nice people, but the darn thing ends up on YouTube, and somebody in Nova Scotia takes offense to it and starts a internet campaign against me. My house gets burned down in the middle of the night, so I try to limit the jokes now. I wish I didn't have to. I love humor. It's even better than math. Okay. Oh, silly me. I'm looking for that inverse function and it's not there. So I'm saving Jorge the trouble of reminding me. Yeah, you told us last time to push the X inverse key. Okay, there's my matrix. That's the inverse. And if I wanted to copy it down on the paper, I could, and I will just because it makes better notes. Actually, every single entry in here in absolute value is a half, right? So how about if I put the half on the outside and then just use ones? Minus 1, 1, 1, 1, minus 1, 1, and 1, 1, minus 1. That's my inverse matrix. And what I would like to do is just left multiply this coordinates, 3 minus 4, 6, by this inverse. And I'm supposed to get the coordinates relative to the basis B. And we can test that at the end. So if I'm really lucky, I think I can just say ANS. I think it'll call this result back up. And then I'm going to multiply it by, oh, darn, I need that entered. That's a 3 by 1. And the thing I'm trying to multiply on the left, the factor on the right is 3 minus 4, 6. Did I do that right? Okay, looks like it's right. Times, I think it might have been faster to do it by hand. Okay, times this, assuming I've pushed all the buttons properly, I get this result, minus a half, 6.5. How about some decimals here? I like that. Minus 3.5. That is the coordinate vector of V relative to the basis B if I've done all the calculations correct. Now, it's pretty easy to find out if it's right, because what it means is if you take minus 1/2 times the first basis vector plus 6.5 times the second basis vector minus 3.5 times the third basis vector, you're supposed to come up with this vector right here, 3 minus 4, 6. So let's give it a try. What is my basis? The basis is this one right here, 0, 1, 1, 1, 0, 1, 1, 1, 0, and then I want to multiply it by these coordinates. Yes, thank you. So this is B in symbols. This is B on the left times the coordinate vector for B relative to basis B. And this is supposed to give me, if my formula is correct, it's supposed to give me the coordinate vector of V relative to the standard basis. And that we can check because we know where we started. So let's try. I have that thing stored in ANS, right? So let me actually move that into a named matrix. I think I can do this. Store, where'd you go? Store. Let's put it in C. Okay, looks like I saved it successfully. Minus a half, 6.5, minus 3.5, that's what I wanted. And I want that inverse matrix to be. And I think I've just got, I think I put B in cleverly enough, A. Anyway, so there's the B matrix there. I want to multiply it by this matrix, which I just stored in memory location C. And I get 3 minus 4, 6. And let's just check. Oh, good. That's where we started. We started with the vector 3 minus 4, 6. That's relative to the standard basis. We did this inverse trick. It's B inverse times the standard basis coordinates gave us the coordinates in the B vector. And then just to check, we said, well, what would that mean? It would mean that if you took these as multipliers on the B vectors, and that's done with a matrix multiplication, it should take you back to the standard basis coordinates, and it did. Okay, so it works. How do you get, okay, so let me rather than use so many darn words, we have a basis which we call S. This is the standard basis. And we have an alternate basis B, which I called B. And I started with a vector named by its coordinates here, 3, -4, 6. I found out that its name in this system B is minus 0.5, 6.5, 3.5. And I found out that if you want to go from standard basis to the alternate basis, you multiply by B inverse. And of course, this means the B matrix, right? And that means the set B. So I'm doing exactly what I warned you about. I'm a little bit sloppy with notation. Sometimes B means the B coordinate system, and sometimes it means the matrix you get from that. Now, I checked it as well, though. And how did I check it? I took the B matrix on the left, multiplied by the coordinates in the B coordinate system, and I ended up in the standard. So this is reversible. You can go this way by left multiplication by B. And now we're running a bit short on time, not too short, but I want to get to the big idea here. So what if you had yet another basis, call it C? Well, this same trick would work. If you wanted to go from coordinates in the standard basis to the coordinates in C, you would left multiply by the C inverse matrix. And what if you wanted to go back? Well, you'd left multiply by the C matrix. And what that means is now we know how to go from here to here directly. And here's how you would do it. If you started in B and you wanted to end up in C, you would do this. You start, whoops, try again. You'd start with a vector in mind, but it's expressed in terms of its coordinates in B. Now, if I wanted to get to C, this is what I would do. First of all, I would multiply on the left by the B matrix. Why would I do that? Because that gets me back to the standard basis, and I know what to do in the standard basis. Then if I wanted to get from the standard basis down to the C basis, I would multiply on the left by C inverse. And since multiplying these two 3x3 matrices would give me another 3x3 matrix, this is, after all, a linear transformation, because you could combine those two to get a single matrix. So that is a linear transformation T. The change of basis linear transformation to go from B to C is this. You left multiply. Now remember, the way it's written looks backwards because we're left multiplying. You first multiply by B, then you multiply by C inverse. And the result will be the coordinates in C. And since I'm off the notes by now, there is really no reason I shouldn't just do this. Let's take another basis here. I'm gonna construct one that I know in an instant is a perfectly good basis. 1, 1, 1, 0, 1, 1, 0, 0, 1. Perfectly good basis. This one here I'm going to call the C vector 1, the C vector 2, and the C vector 3. And this, if you stack them up as columns, that's my C matrix. So really, you know, don't let yourself get tangled up. I'm doing over here exactly what I did over here. I'm just another example with a different basis. Okay, so I know ahead of time that this C matrix is going to be useful. That's this 1, 1, 1, 0, 1, 1, 0, 0, 1. And where did that basis came from? I just made it up. And I wanted ones and zeros because they're pretty simple. I will probably, at least for some transformations, I'm definitely going to need the inverse. So let's go ahead and compute that ahead of time. And this time I will put C in C so I don't get too confused. Okay, it's this guy right, where are you? Right there. So the rows are 1, 0, 0. Second row, 1, 1, 0. Third row, 1, 1, 1. And let's get out of here and see if it worked. Yes, that's what I want. Now, I think I put my B matrix in location A in my calculator. And that might not confuse you, but it does bug me. That's something different. I pulled up B rather than C. Let's try again. Yeah, that's my B matrix. So rather than allow myself to be hopelessly confused later on, I'm going to do this. Matrix A, I'm going to store that in matrix B. Okay, so when I have B on my paper, it's going to be the B matrix in the calculator. And when I have C on the paper, it's going to be the C matrix in the calculator. And I hope that will help. All right, so let's finish the calculation. So I know this, the coordinates 3, -4, 6 in the standard basis refer to the same point as the coordinates -1/2, 6.5, 3.5 relative to the basis B. Well, you could ask this question as well. Well, what would the coordinates be here in C? Well, we know. If you want to, what we're asking for then is this, the same vector V, but relative to C. How do you do that? So down here, I want the coordinates of V relative to C. Well, the answer would be this. Well, first of all, let's figure out how to get back to the standard basis. Whoops, no. I know this one in the standard basis. So what I would like to do is to take the coordinates in the standard basis, 3, -4, 6, and the diagram tells me that if you left multiply by C inverse, that should give you this guy. And that's a lot to write, so I'm just going to say C inverse for now. And now I don't know C inverse, but I can get it. Oh, I just contradicted myself. Not long ago, I told you up to 7 by 7 I can do instantly from memory. That was a lie. Okay, so here's C inverse. So 1, -1, 0, 0, 1, -1, 0, 0, 1. Okay, so what are the coordinates of this point relative to the C basis? Well, the answer is you take C inverse, which I've now just figured out, or really my calculator figured it out for me. And the recipe says, in general, you want to multiply on take these coordinates, multiply on the left by C inverse. that should give me the coordinates in basis C. So, so I've got that answer there. So I've got, maybe just to make the video better, C inverse, then I'm going to multiply by this 3 minus 4, 6. Did I store that in A or not? I can't remember. No. Let's put it there. And hopefully you're catching on to why I like MATLAB. I just type it in. Okay, C inverse times this vector right here is 3 minus 710. Okay, and I hope that's right, but it's easy to check. If I took this 3 minus 710 and left multiplied it by C, it should get me back up. 3 minus 710 left multiply by C, it should take me back to this one right here. So let's try it. I want to take C, multiply by the previous answer. I hope it hasn't been lost. 3 minus 4, 6, sure enough, it worked. So that works. This is the matrix representation of V relative to C. And now, finally, we're ready for the punchline. What if you wanted to go direct from B to C or from C to B? You can with matrix multiplications. Let's suppose we wanted to go from B to C. Wanted to go this way. Well, it's just like driving on a highway. There's more than one way to get there, right? You could go direct, but then another option would be this. If you started with the B coordinates, multiply them on the left by C, and then on the left once again by C inverse. So if I take the B coordinates, which are minus 0.5, 6.5, 3.5, multiply them first on the left by B, and B is, where is B? I lost it. Oh, here it is. Previous page. This is my B basis. So 0, 1, 1. 1, 0, 1. And the whiteout vector, 1, 1, 0. So if I start in coordinate system B, multiply on the left by the B matrix, that's going to put me back to the standard basis. Then if I multiply on the left by C inverse, and I hardly left room for that, C inverse, which I know now, I've pre-computed it, 1, 0, 0, minus 1, 1, 0, 0, minus 1, 1, and I need a bracket there. That should get me to the C coordinates. So let's double check, see what we got in here. I think I have B and C stored. B is stored. C is stored. And now I just need to store these coordinates in the B system. So I think I don't want to put that in C. I will put that, why don't I put it in something I'm not using, F. So that'll be 3 by 1 and minus 0.5, 6.5, 3.5, that's an F. Okay, so it says you start with the C inverse matrix. Let's write this in symbols. Well, when you're writing it down, it'll be on the leftmost, C inverse matrix, then the B inverse, then the B matrix, then the coordinate matrix in B, and this is supposed to yield the coordinate matrix in C. So that's what I'm doing. All right, so on the calculator, matrix C, take its inverse, multiply by matrix B, then multiply by the vector which I stored in F. (10 minus 7, 3). Oh, I have these in reverse order. Did I reverse those last time? This is a real problem because I am not kidding here. I really am dyslexic, so it's hard for me to tell. What did I do? Oh, 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 oh. Look here. Negative 3.5, negative 3.5, positive 3.5. So there's an error there, which produced an error here. Okay, let's try it again. Go back to matrix F and minus 3.5. 3 minus 7, 10. Aha, and that's what I wanted. So, wow, that was a strange coincidence. 3 minus 7, 10, which is the coordinate. I'm doing just exactly what I told you not to do, right? Sorry. So 3 minus 7, 10 is indeed the coordinates here. And how do you get direct from here to here? You multiply by, in terms of the order of multiplication, you multiply by C inverse on the left first. Having done that, then you would multiply by, I said it backwards. You multiply by B first. Why? Because you're transforming to the standard basis. Then you multiply by C inverse to get you back down here to C. So what we're saying is that transformation, the transformation that takes you from the B coordinate system to the C coordinate system is accomplished by this calculation. You multiply, you start with your coordinates in V. You first multiply on the left by B, and what's that doing? That's putting you back to S, the standard basis. And then you multiply by C inverse, and that's putting you back to the basis C. So this is the same as this. Multiply on the left by B, follow that up by multiplication by C inverse, and it will get you to coordinate system C. Okay. Now, I don't know about you, but for me, this is really easy to get tangled up. So, you know, not every linear algebra book does it, but I recommend thinking of it in terms of, this is called a commutative diagram. It's a thing that algebraists use quite often. And you can see why. This gets really kind of complex after a while, right? So if you know how to create and read the commutative diagram, then you will probably not have trouble. And by the way, once you have one of these arrows labeled, it's pretty easy to label the other one, because here's an identity. Let me, rather than get tangled up with the A's, B's, and C's we've already got going on with our rolling around in our brains. If X and Y are matrices, the inverse of the product XY is Y inverse X inverse. So you flip the order and apply the inverses to each one. So if this C inverse B takes us from left to right, then its inverse will take us from right to left, which in this case would be B inverse C. Okay, and there's a couple of exercises that ask you to make these diagrams. So here's a couple of bases. Here's a vector in one of the, here's the coordinates in one of the spaces. Compute the coordinates in the other spaces. Draw the diagram. Label the arrows with the matrix multiplications. And honestly, by my way of thinking, the diagram with the arrows in the matrix multiplications kind of comes first, because that tells me what to do to get from one vertex to another on the diagram. I'm sorry, it's hard for me to hear. The question is there a way to go from one non-standard basis to another non-standard basis without traveling through the standard basis? The answer is yes, but in effect, you are traveling through the standard basis. If you gave me this and this, B and C, and you said to me, okay, would you please construct for me a matrix T so that left multiplication by T will get me from B to C, and left multiplication by T inverse will get me from C to B. I'd say, absolutely no problem, give me a minute. And then I would take my paper, move it out from under the camera. I would compute C inverse B, I would multiply them together, and I would say, and then since I like to be theatrical, I would do something like the mentalist pose. And then I would write down the product, which I had in fact done in MATLAB. Okay. Now I say that in kind of a funny way, but it's actually not completely trivial, because what this does, besides giving me practical ways of computing these transformations, at least for small matrices, you know, if these were like 1,000 by 1,000 matrix, this wouldn't be so nice. But for small matrices, it it at least tells me there is a matrix that will work, right? So I could maybe use some other strategy for figuring out what the matrix is. But for small matrices, by far, the easiest way to do this is to go, at least the first time, to go through the standard matrix. And once you've got that product, then you're good to go. You don't have to mention that S anymore. Okay, anybody else have a question? Okay, I got off script a bit, but I think I've actually done okay for following. That was this part. Actually, I should be clear. I did not pay Tommaso $10 ahead of time to ask me that question. It really was in the outline. How do you go direct from B to C? And the answer is just what I said. You know, you do this matrix multiplication if necessary in the background. And what am I doing with my pages here? I don't know. And then you can draw this all out in a diagram. And if you, by my way of thinking, it's easier to draw the diagram because it guides you in the calculation. And then, you know, I just kind of said what I said there already. And I actually did an example like this. And it's this thing right somewhere. Oh, right here. That's the example, right? So if you have a couple of bases in mind, alternate bases in mind, then you, and given the coordinates at any one of these vertices, you can compute the other two just by matrix multiplications. Okay, and in order to make this of some value later, I probably should fill in what the B is, this B that we started with right here. So I'm just going to, while I'm here, before I forget, this is the B matrix. So when you, if you download the notes later, it'll hopefully make some kind of sense. Okay, that pretty much takes us through page 7. And these were just examples. So let me see if there's anything else big I need to tell you about. Oh, this is kind of a more abstract way of thinking about it here at the top of page 9. And that is, at this point, we really start driving home the idea that there is a distinction between coordinates and a vector. So a vector is sort of an idea all by itself. And then you could use different bases, in different bases, it could have different coordinates, right? But it would still be that one fixed vector. So the point is this: if you see a vector ABC, you know exactly what that means, how you interpret that. You have to know what the basis is. So for instance, if we were working in the space of second and lower degree polynomials, it might stand for a plus bx plus cx squared, a function, a quadratic function. Or it might mean the standard thing, the point in 3 space with the standard basis with the coordinates x, y, and z. Or maybe it could be a pretty short Fourier cosine series. You just don't know unless you're given the context. So the idea is coordinates are always relative to a basis. In reality, in order for coordinates to make any sense, you have to be given the coordinates and the basis that goes with it. The other point I really do want to make is this: keep in mind when we were doing these calculations I was, it was implicit in the way I was writing it, but I never stated it. When I said, well, what's the standard basis for R3? It's E1, E2, E3. That comes not just with standard vectors, it comes with standard vectors in a standard order, right? And if you move that order around, it would also change the coordinates. So we never said it officially, but in reality, we're not just working with bases here, we're working with ordered bases. So if I take in standard O3 space, so I have standard basis vectors 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, the point with coordinates 1, 2, 3, it means 1 times the first standard basis vector, 2 times E2, and 3 times E3, right? But if I just permuted the order and I said, okay, now my basis is E1, E3, E2, it would flip all of those second two coordinates for every point in the space. So, you know, it's a little bit more finicky than I actually said verbally earlier. But, you know, we can all handle that without any problem, I think. Okay, now the last thing I want to mention is this, and that is just what I was saying. If you modify the basis, then you are going to modify the representation by matrix. And that's true for coordinates. It's also true for linear transformations. And the reason it would matter, let's go back to this situation here where, you know, I'm flying along in my fighter jet because I'm late for work and I got to get there quickly. And we have this transformation where the pilot is doing a roll. Okay, now in the coordinate system where, say, the x vector is pointing in the direction of travel, that is a very simple transformation. Over a period of time, you're just doing a rotation, right? But if you take it relative to like ground coordinates with, you know, an axis along east-west and an axis along north-south and an axis in the vertical direction, now if you were going to describe that with a matrix multiplication, and you can, it would be a very much more complicated matrix. So if you think about it, one of the ways you could attack that kind of problem would be this. You could say, well, the transformation I'm trying to create has a really simple representation in a nice coordinate system. Namely, it's just a rotation matrix. And it turns out those are actually real easy to make. Something like you have some cosines and sines in there. That's all it is. So, so if you could first transform to the convenient coordinate system, then do your rotation with a simple rotation matrix, then transform back to the standard coordinate system, you would have a recipe for creating complicated matrices for actions that are relatively simple in a nice coordinate system. And the only reason I say that is it turns out to be really common in applications of linear algebra in science and engineering, that you want to transform the coordinate system to make the transformation simple looking and like a rotation or just a stretching along one of the axes or something like that. And it turns out that if you make it as simple as you can, in many cases, the transformation is a diagonal matrix. And by diagonal, I mean something like this. It has non-zero entries along the diagonal and zeros everywhere else. Now, when you can do that, we say that the transformation matrix is diagonalizable. And at this lesson, we're not going to describe how is it you find out if a matrix is diagonalizable or not. And if it is, how do you do that? That's for later. But I just want to point out that sometimes by lucky accident, you can come up with a matrix P so that P inverse times the original matrix A times P is a diagonal matrix. Sometimes you can do that. And when you can, it's really, really handy in some contexts. Why? Because you've taken what looks like a complicated transformation and turned it into something simple, like a rotation or a stretching or something like that. So I'll let you read that detail, but it's all spelled out in this example, which at least is written better than I can write it. Now, there is one homework problem that says something like verify that the matrix P diagonalizes the matrix A. All you're supposed to do is this. First of all, use technology to find P inverse. And then you compute P inverse AP. And if P diagonalizes A, you end up with a diagonal matrix. Okay, that's all there is to that problem. I'm telling you the way to diagonalize it. So here's P, so compute P inverse and compute P inverse AP. If it comes out to be diagonal, the answer is yes, it diagonalizes it. And if the problem says verify that P diagonalizes D, I think it does. And if it doesn't, then the answer is, Professor, you made a mistake on this problem because it does not work. All right, because there's nothing else for you to do. I didn't tell you how to compute P. I just said verify that it works. Okay. All right, well, that's it. And I think I did actually cover this pretty well, though I wasn't always looking at the pages. All right, that's it for tonight. If you want to hang around and ask questions, you're welcome to, but otherwise, we're done with class. Tonight, the next hand-in homework assignment is going to be posted. That is due on Tuesday, but we really have 2 weeks that we're working with here because I didn't pick one up this week. I am also going to publish the first half of homework assignment number 3, and I'm going to give you like an extra couple of days to get that one turned in. So Tuesday is the homework assignment that's going to appear online tonight, and then Thursday of next week is going to be the first half of homework assignment 3. Okay, so when you do it, I don't care. I just need the number 2 next week on Tuesday, and I need the first half of homework assignment 3 on Thursday. All right, have a great night, and I'll see you on Tuesday.